Hello and welcome to this presentation of SenseBERT driving Sensent into BERT. Today we will talk about SenseBERT, a recent paper based on BERT architecture. In this video I will present you those subjects. To make sure everybody could understand this presentation, let me offer you a quick recap on word embedding. The objectives of a word embedding is to represent a word as a vector. What is expected is that a word with a similar meaning should have a low vector distance. For example, dog and cat should be closer than dance and tree. The limits are how to deal with ambiguity. The word bass means an instrument of music, but also a kind of fish and the deep voice of a choir. So, what's BERT? If you never heard of BERT, let me offer you a quick description. BERT is based on Google Transformers, developed in 2017. It allows to understand the semantic of language from the context by computing word contextual embeddings, which are embeddings that can understand the context of a word but looking at the left and at the right of the word. This is why the name of BERT is Bidirectional Encoder Representation from Transformers. It used the distributional hypothesis. The distributional hypothesis is the idea that words that occur in the same context tend to have similar meanings. BERT has two important steps, a pre-training step and a fine-tuning step. Let's start with the pre-training. Given a database of natural language like Wikipedia, we can extract sentences and feed the neural network with the sentences. But here's the trick. You have to mask some words. The pre-training consists to predict what are the masked words. For example, here in the sentence, the doctor ran to the emergency room to see mask patient. Guess the word. Hooray! If you answer one of those propositions, it means that your English is probably at least as great as mine. And this little exercise is exactly what BERT is trying to learn. Nota bene, on top of mask words prediction, there is also the next sentence prediction, but we won't talk about it in this video. Anyway, how does BERT guess the masked word? Let's look further. This is the structure of BERT. As I said before, the input is a sentence with a few masks on a few words. A sentence is a sequence of n words, and a word is a one-hot vector of size dw, which is the size of the vocabulary. W is a mapping to encode word in the dimension of the encoder, which is d. The dimensions of w are d times the dw. P are the positional embeddings of each word. The intuition here is that adding these values to the embedding provide meaningful distances between the embedding vectors. The encoder is a deep learning model with attention mechanism. I will not talk about it in detail, so let's just consider it as a black box. This black box receives n vector of size d and will output n vector of size d. Each of these vectors correspond to a word, and we expect that multiply this vector by the transpose of W with a softmax layer will give a distribution of probability of words. The distribution of probability is Y word, and its size is the size of the vocabulary. In this example, we can see the prediction for the two masks given the sentences. The doctor ran, probably to the emergency room to see maybe his patient. The selection here are the most probable possibilities, but you have to understand that there is a probability for every word of the vocabulary, though the probability for fish here is pretty weak, for example. The encoder has one output for each word, but we won't compute the softmax for each word, but only for the masked word. The reason is that we want to learn to predict an unknown word. Known words are already encoded in the word contextual embeddings. On the top right corner, you can see the loss. The loss is minus log p of w given context. And pw given context is the exponential of the correct word divided by the sum of the exponential of every word. Once the pre-training is done, yay! We can move on the next step. In order to fine-tune our model, we have to delete the two last layer, the softmax and the transpose of W. Then we add a feed-forward neural network on the output of the encoder. The structure of the model is now finished, and we can fine-tune BERT in a supervised way to do an NLP task. In this example, we want to learn a model to do spam classification. BERT receive text inputs, outputs, word contextual embeddings, which are used as inputs for the feed-forward classifier that will say if the text is a spam or not. As the text say help Prince Mayuko transfer huge inheritance, I think the probability of being a spam is pretty high, right? Great, we are making some progress. So, after this consequent introduction, let's get back to SenseBERT. What's new in SenseBERT? As you can see here, SenseBERT seems pretty close to BERT, except that it predicts also something called a supersense. If you feed BERT with done cooked bass on the grill, we expect that all of the Y word for each word correspond to our words. And if we feed SenseBERT, we expect the same thing, but also to have the supersense of the word. Just to make sure everything is clear so far, Y word is a distribution over all of the word. The word with the highest probability is the word that BERT will predict. Y word concat is just the concatenation of all of the prediction. The interesting part is that bass has been understood as food, which is a good news, because a bass can be an instrument of music, a voice, and a species of fish. And in the context, I think it's the last one. Whew. Right now, if you follow what was going on, you might have a few questions. What's a supersense? What is S? What is M? For BERT, we use unsupervised learning by masking a word to predict, but here, how do we know what's the real supersense to predict? Instead of answering your very relevant question, let me answer to another question. What is WordNet? WordNet is a lexical database that started to be developed on the mid-80s by Princeton University. Among all the information, we can find what's called, well, lexical file info, but we will call it Supersense. Now, let me explain you the notion of supersense. A supersense is a category for words. It represents the different senses a word can have. For example, star. It can be an object, a person, a shape, and also communication if you use the asterisk, for example. And it can also be a verb. Thanks to this supersense, we can go forward the true semantic of words. In WordNet, it exists 45 categories, 26 for nouns, 15 for verbs, 3 for adjective, and only 1 for adverbs. But how these supersense are related to BERT? To understand things more easily, let's focus on this part. SenseBERT receives as inputs a sentence of n words. Each word is of size dw. W is a matrix of dimension d times dw. S is a matrix of dimension d times ds. W and S are useful to allow the pre-embedding of each word to be in the right dimension in order to be an input for the encoder. Just to remind you, the DW is the size of the vocabulary and ds is the number of supersense. We multiply each vector x by w and we obtain n vectors of dimension d. Then we multiply smx. What is m though? M is the fixed matrix created from word nets representing the supersense of every word. For example, the word star is a person, a way of communication, a stative verb, etc. It is done in a binary way. It is of dimension ds times dw, as there is a size of dw words and 45 supersenses. The advantages of this matrix is that if we multiply the word x by m, the result is the column of the corresponding word. The reason is because x is just a one-hot vector. For example, the multiplication of m by the one-hot vector of star is the column of star. Pretty cool, isn't it? As S's dimension is d times ds, then the dimension of smx is just d. P is the positional encoding vector. It already exists in BERT. It is useful to understand the position of word in the model. It is of dimensions d. And this is pretty cool, because the sum of vector of dimension d is a vector of dimension d. And this is perfect, because now we have n vectors of dimension d that will go as the input for the encoder. The encoder will receive each word pre-embeddings and then apply attention mechanism. In outputs of the encoder, we have finally the word contextual embeddings. And if we multiply it by the transpose of W and S with a softmax layer, we have the probabilities for masked word prediction and also for supersense. Oof. If things are not very clear in your head, do not hesitate to go back and see again what you missed. So, how the loss work? The loss for word prediction is minus log of probability of W given the context. It's the same as for BERT vanilla. If the softmax of wrong word is too high, we'll have an important loss. Probability of W given the context is the formula at the bottom left. W is the word that we want to predict, while W' are all of the other words that we do not want to predict. Now for SenseBERT, we want the loss to increase the softmax of all of the senses belonging to AW. AW is just the set of possible supersense for the word W. So, the loss might be minus log of probability S belonging to AW given the context, or minus log of the sum of probability of S given the context for every supersense S belonging to AW. It consists to compute the sum of the probability of having the sense given the context. As L allowed SLM pushes the network in the right direction, minimizing the loss could result in the network becoming overconfident in predicting a strict subset of the allowed subsenses for a given word, a collapse of the prediction distribution. This is why SenseBERT added a regularization term. It will avoid the other probabilities to collapse. The loss with regularization term is minus sum of 1 divided by the number of supersense multiplied by log of probability S given context for every supersense S. So the final loss would be the loss allowed plus the loss with the regularization. Okay, that's a lot of math on the screen. Do not hesitate to press pause to make sure everything's clear. We are almost done. Congratulations! So, what's so great about it? Does it bring any more information? Is it really useful? The supersense bring more knowledge and allow to generalize notion with similar sense but not the same way of being written. SemEval-SS is a variant of SemEval word sense disambiguation, which is a dataset used to evaluate the comprehension of the language. Here, the evaluation consists to predict a category of word. If SenseBERT is not better than BERT, then instead of using SenseBERT, we could just fine-tune BERT to predict the supersense with the word contextual embedding and concatenate the outputs. For example, for the sentence, the team used a battery of the newly developed gene probes. BERT predicted that battery was an artifact, while, as predicted by SenseBERT, it was a group. Wording context is also a method to evaluate the comprehension of the language. This evaluation consists to predict if the meaning of two words in different contexts is the same. For example, is the word kick in the kick must be synchronized with the arm movement, the same as a sidecar is a smooth drink but it has a poor kick. It is not the case because the kick in the first sentence is a kick done with the foot, while the other is figurative, meaning that the alcohol is strong. As we can see, the score obtained on SemEval is way better on SenseBERT than BERT Vanilla. SenseBERT Base is even better than BERT Large on this task with 75.6% on SemEval SS Frozen, again 67.3%. Frozen just means that we didn't update the parameters while training, unlike the fine-tuning. It is useful to realize that the pre-training is important if we want to have the information of supersenses. We can't use BERT if we want the information of SenseBERT in a good quality. On top of that, SenseBERT reached the state of the art and goes even beyond with more than 2% better. To be more mitigate, we can notice that the increase in performances when the model is fine-tuned is not so high. GLUE is the General Language Understanding Evaluation. On average, SenseBERT is better than BERT, but in my opinion, the progress is not spectacular. Oh, looks like this presentation is over. To conclude, SenseBERT is a smart idea. The score is obviously better, and it makes sense as it brings more information thanks to weak supervision from WordNet. The performance are not spectacular, as I said earlier. Though, it is still something, and it makes sense to use SenseBERT instead of BERT if you want to work on natural language processing. Also, the idea of adding a weak supervision can lead to other solutions in the future. Maybe another supervision with another database will increase a lot the performance of BERT. We'll see. And this is the end of my video. I wanted to thank my teacher Carlos Ramish and Alexis Nasr for their precious advices and their implication in the making of this video. I hope that you learned something. Goodbye.